what happens next is, okay, now I've identified the world. I have a simple world model. I know the events in the world and I have given them labels with respect to my own existence. But now I want to become, if you want, optimal. I want to react to this world in an optimal way. So I need plans for actions. I need to assemble plans for my actions. So we say now, well, over this simplified description of the world that I have, I can start in my contextual layer where I have different mechanisms of memory. I can start to look at how things relate in time, right? I can say, well, if I'm navigating from A to B to C, there's an order. I can now try to store or commit this order to memory so I can reuse that for future reference. Okay, so, which means the DAC architecture is a bootstrapped architecture. It starts at the reactive layer, combined with mechanisms for learning and for memory, but then it generates content, if you want, to its memory structures that in the end represent plans for action. Okay? So DAC is solving what we call the H4W problem and the problem of priors. What this essentially means is you want to know how to act, so how, you want to know how, but your actions have to be satisfying 4 W's. So you have to know where to act, why, for what motivational reasons to act, on what object are you actually reacting to, and what are the particular affordances of these objects, and when. You have to know the timing of your reactions with respect to the dynamics of the objects that you deal with. And the problem of priors is trying to say, well, in traditional artificial intelligence, and also still in a lot of machine learning that's going on, people would tell you, look, if I have a predefined state space of the world, then I can give you a policy. But that means that some of these solutions are facing this problem of priors, because where does this labeling of the state space come from? And what we're proposing in DAC is that that problem of learning the policy should be addressed in combination with the problem of how you solve and develop your state space. So actually we're saying the adaptive layer is largely acquiring the state space out of the interaction with the reactive layer, and the policies are then generated at the level of this contextual layer. So in that sense, DAC is unique of providing this more integrated view on learning and in the end optimal decision making. So this is a bit more a detailed view on this DAC architecture. So if you want, at the core of our memory structures is the idea that we have couplets of sensory and motor states, so stimuli and responses. That means when I'm acting in the world, I'm perceiving this world, I detect stimuli, I'm responding to these stimuli simultaneously, so these are now my atoms of representation, and I can store these in the order that I'm generating them. Okay? Then subsequently what we do, I can store these sequences in my long-term memory as long as I achieve goal states. Because if I achieve a goal state, I find food, I escape from a predator and what have you, I could say, well, whatever I did in the recent past must have contributed to this success. So there must be some order to the sequence that I want to conserve. And now what's important here, that's expressed in this expression here of E, which is called expectancy, or also the prototype. The sensory representations we store in memory are not just snapshots of the world. This is a very important distinction in our architecture. The sensory representations we store in the world can really be seen as percepts. It's how I interpret as an acting organism the sensor states that I encounter, which makes an important difference, because that means that when in the future I start to make predictions on the world from my long-term memory, I'm using the same currency, the same representational currency as preceding layers of the architecture. So they can now start to parse sensory events in the world in parallel. What we have already shown in the past is that DAC is optimal in a Bayesian sense, which means in some sense you can say that DAC is optimally using the knowledge that it has acquired. However, how we obtain this result is by showing that if I take the foraging task where I want to maximize the number of targets I find, and I want to minimize the number of collisions I suffer, then I can redescribe this task in Bayesian terms, because there are elementary events in this task, like the objects I might encounter or the targets that I might encounter, and I can now identify the dynamics I should follow to optimally exploit such an environment. And what we've shown in the past is that the dynamic equations of the model are equivalent to just a pure Bayesian description of that foraging task. So that was the starting point on the grounds on which we believed we could now make this next step to generalize DAC towards optimal foraging, and that's what the whole Synthetic Forager project is now investigating. So the overall architecture, to finish up the overview, in the overall architecture, which is sketched here, we have added a bunch more of boxes. We will describe a number of these boxes in more detail, but again, what we should look at are also the three columns we have here now. So essentially we're saying we have one column in our architecture that is exclusively dealing with the outside world. It's exclusively dealing with sensation, perception, and forming memories of events in the world, my episodic memories. There's a core column that very much represents the organism itself. If you want, this is the self with its needs, its drives, its internal states, and in the end the value and utility functions that are built on these. Like, what do I need, what do I want with respect to my own survival? And the third column is then very much, if you want, the interface between the self and the world in terms of the actions that I'm generating, in terms of my plans, the actions, intentional actions focused on the world, specific behaviors, might be more reactive, and how this is then mapped onto the end effectors that help me to actually behave. So what we're going to look at in more detail now is this notion of allostatic control. How can I regulate my behaviors with respect to my needs? We're going to look in more detail about how perception and action at this adaptive layer both essentially depend on prediction, and we're going to look in detail how I can perform plans for action at the contextual level. And lastly, we will look in some detail about how specific structures in the brain, in particular the hippocampus, are suggestive for this idea of an integration of sensory states and actions as an integrated couplet, as a primitive for memory and planning, is consistent with their understanding of how integration of information happens in the hippocampus. So that's the program for now. Thank you very much for your attention.